While we are becoming familiar with identifying electrolytes and non-electrolytes, it may be helpful to use a flowchart type method. And here we have a flowchart that can be used to identify whether a substance is a strong, weak, or non-electrolyte. So we know that a substance will be a strong electrolyte if it is an ionic compound. So the first step in my flowchart is to identify ionic or molecular. And this is something that we have done since chapter 6. So we know that an ionic compound consists of a metal and a nonmetal, with one exception, that is ammonium, serving as my cation, so something like ammonium chloride or ammonium nitrate. You have to be able to recognize the NH4 as a cation and will be one partner in that ionic compound. Our molecular compounds consist of nonmetals and other nonmetals. We know that ionic compounds are strong electrolytes because of the ability of solutions containing these ionic compounds to conduct electricity. Electricity is moving charges. So in order for some substance to conduct electricity, it has to have charges present in order to carry a current. So having these charged ions, say sodium and chloride, allows the substance to conduct electricity. And when we think about the amount of conductivity, the amount of current that a solution can carry, is related to the concentration of ions in solution. So the more ions there are, the more highly conductive that solution will be. So if we have sodium chloride producing Na plus and Cl minus, we can compare that to MgCl, which would produce magnesium 2 plus ions and 2 Cl minus ions. So the fact that we have 3 ions instead of 2 ions means that the magnesium chloride will be a better conductor of electricity because there are more ions in solution. Molecular compounds like water and ammonia and sugar, these are compounds that will not conduct electricity because they are non-electrolytes. There will be 0 ions in solution. So you might be wondering, why then does your hairdryer and other electronic devices give you warnings about keeping away from water if water doesn't have any ions in it? Well, pure water doesn't have any ions in it. That is, water that has been distilled or purified and to deionize it. So deionized water or pure water will not have any ions present. Now the water that comes out of your tap has been passed through the ground that contains a lot of different materials, including ionic compounds like lime, calcium carbonate, and salt, sodium chloride, and magnesium sulfates. So there's a lot of minerals that this water passes over and dissolves some of them. So your water that comes out of the tap will have some amount of ions in it. And the presence of those ions allows it to conduct electricity, and hence the warnings on your electronic devices. Okay, so now we know how to identify ionic versus molecular compounds, so let's go on to the next step of my chart. Let's say we have a molecular compound. Now our question is it an acid, a base, or neither? And to answer this, we have to understand how to identify an acid versus a base with respect to a compound structure. So let's start with the acids. So if my compound is an acid, we can classify acids into a strong acid category or a weak acid category. And much like strong electrolytes and weak electrolytes, strong acids completely dissociate in water, while weak acids only partially dissociate in water. There are just 7 strong acids that will completely dissociate into water. And these 7 are compounds that you're going to need to memorize, essentially. So get these under your belt. There are, in the halogen column, HCl, HBr, and HI, sulfuric acid, nitric acid, chloric acid, and perchloric acid. So these 7 are strong acids and will completely dissociate. 100% of the molecular acids here will dissociate into ions in solution. Now, a weak acid is any other acid. Okay, any other acid. How do we recognize an acid? Well, typically it begins with an H. So there are some inorganic acids like H3PO4, HF, HCN. These are all only going to partially dissociate in solution. An organic acid can be identified by the carboxylic acid functional group. We saw acetic acid as an example before, but any organic acid having this functional group, the carboxylic acid, will be considered to be a weak acid. Only some of this proton will be lost when it dissolves in water. Walking through the strong versus the weak acids answered that third question in our flowchart for us as well. So if it's a strong acid, one of those 7 acids that I showed you, it will be a strong electrolyte. And if it's neither one of those, it's any other type of acid, it will be a weak electrolyte. Now let's talk about bases. How do we identify a base? Because in that second question, we had to identify acids, base, or neither. So what is a base? A base is something that will, by definition, form OH- in solution. And we saw the example of that with ammonia. NH3 mixing with water will produce NH4+ and OH-. And the production of OH- here is characteristic of a base. We again are not going to explore this acid-base concept in depth, but it's useful to be able to identify acid versus base according to their structure for the purpose of identifying electrolytes. So this ammonia is analogous to our organic amines. So anything with an NH2 group, or if we have an NH group, or just an N, right? Depending on whether it's a primary, secondary, or tertiary amine group. All of these have lone pairs that can acquire a proton and become charged, giving hydroxide in water. So all of these amines will be weak bases. You may be familiar with some strong bases, and strong bases are all metal hydroxides, so some metal OH. Okay? This could be sodium hydroxide, it could be magnesium hydroxide. And these group 1 and group 2 metal hydroxides are all strong bases with the exception of magnesium hydroxide and beryllium hydroxide. These compounds do not dissociate 100% into ions. So do not include these in your list of strong electrolytes. Those are exceptions. And it's easy to identify this as a strong electrolyte because it is an ionic compound. So we don't have a separate flowchart step for this because this gets weeded out in step 1. Is it ionic or molecular? So our strong bases are all ionic compounds. Let's summarize our strong versus weak versus non-electrolytes. Our strong electrolytes are going to be salts, ionic compounds containing metal and a nonmetal, with the exception of ammonium cations paired with other nonmetals. We also have strong acids and strong bases. Strong acids, there are 7: HCl, HBr, HI, sulfuric, nitric, chloric, HClO3, and perchloric, HClO4. And the strong bases, remember, are ionic compounds as well, so we don't necessarily need to explicitly list those as a separate category. Weak electrolytes, on the other hand, are weak acids. And the inorganic acids, the molecular formula typically begins with an H. H3PO4, H2SO3. Weak acids. Anything with a carboxylic acid functional group. And our weak bases are anything with an amine functional group. Now, when it comes to non-electrolytes, our non-electrolytes are literally everything else. So if we think about classifying non-electrolytes according to functional groups, which functional groups would be considered non-electrolytes? Well, alcohols, aldehydes, ketones, esters, amides, ethers. Other hydrocarbons are considered non-electrolytes as well. Those CH bonds are not going to be lost to form carbon ions in solution. It just doesn't happen. If you have any questions identifying strong versus weak versus non-electrolytes, please let me know. Thank you for watching.